So we're up to question 3 of the mock. I'm pretty much going to stop telling you that it's on the mock because it'll be in a little folder marked mock. So question 3. The photograph shows a flower of the wheat plant, and already I'm thinking, okay, these are everything hanging outside of a flower. This may well be in colour, but I'm not sure it was. This looks like the sort of keel bit. These are the feathery stigma, and these are the anthers hanging out in the wind. Name the parts labelled P and Q. P, anther. Q, stigma. Calculate the actual length of structure P. So, we've got a scale bar. We effectively want to know how many times the scale bar goes into this. I'm just going to measure that. So that is 29 millimetres long. Remember, don't round up thinking, oh, the examiner meant to do that. No, they probably didn't. They probably just, stuck a line in. And it's, you might get away with 9 or 10 millimetres there. I'm going to go 9. And then we need to multiply it by the actual length of the scale bar. Now we know how many 1 millimetre things there are in there. So, trusty calculator, 29 shared by 9 equals, times 1 will be 3.22. I'm going to just stick with the old and I'll just check that again. 29 shared by 9 equals 3.2. I'm just looking at the mark scheme actually, and it says 3. It says 30 shared by 10, so there we go. But ours has been photocopied and scanned and all sorts of things. Describe 2 features of the flower which suggest that it is wind pollinated. So obviously you can't just go, oh, everything hangs out. But we can put that they're outside the flower. So anthers and stigma are outside of the flower. I'm also not going to write dangling in the breeze. And I'm going to put stigmas are feathery. So remember that in a insect pollinated plant they tend to be sort of rounder and more sort of sculpted surface. Stigmas are feathery. I think those are 2 real giveaways. If it was a colour photograph, you might be able to comment on the colour of this bit here being dull, but I'm not sure it was a colour photograph, and you haven't got one anyway, so there we go. The diagram below shows a wheat grain. So it's got endosperm, it's got an embryo, it's got a tester and an ovary wall. And the presence of that tells me that it's a fruit. So, use information shown in the diagram to explain why the grain is more correctly described as a fruit rather than a seed. So a fruit has an ovary wall. Whereas the seed only has a tester. A wheat grain has ovary wall and tester, and it's a fruit. Phew! Explain why the events taking place in the embryo sac of a wheat flower are described as double fertilisation. So remember, double fertilisation is 1 male gamete fuses with the egg cell Oh, with the egg cell. So we had a little diagram like this, didn't we, with all the antipodal cells, the egg cell, the synergids and the polar nuclei in the middle. Remember, one of them went there and one of them went there. To make a gamete. Notice I'm not calling this fertilisation of the egg cell, I'm literally saying what it does, it's fusing. And one male gamete fuses with polar nuclei to form the endosperm. I think I'd be tempted if I was an exam to say that there are two male gametes, just to make it really clear. But I'm not going to do this. Photograph shows a flower of the field mustard plant, which is that's the yellow rape that you see flowering in about May time. So, diagram 1 shows the classification of wheat and field mustard and their evolutionary relationship. Whoopie-doo. Right, each branch on the diagram represents a clade. Mark on X where wheat and field mustard share a common ancestor. I think it's probably a good idea just to... There's the wheat, there's the field mustard, common ancestor all the way back to there. Easy. In modern plant classification systems, hierarchical groups like divisions and classes have been replaced with unranked clades. Yay! But orders and families have been retained and have names ending in ales, so that's the order, and acia, that's the family. So, B wrapper, there we go. Brassica, family Brassicaceae, order ends in ales, so that's Brassicales. I'm just copying the spelling across. And we've got rosids, and then unranked, this is a dicotyledon. And they've made it plural over there. So, this one, I'm going to work back again from T. Aestivicium, genus Triticum, and then we've got the one that ends A-C-E-A-E, so that's however you pronounce it, Poaceae, perhaps. And we've got Poales, and then unranked, between monocotyledons and Poales, melanids. So that looked a lot more complicated than it actually was. You're just reading straight from a diagram and copying it across. Easy peasy. Right. Using the information given and your own knowledge, oh here we go, describe how the seed of a field mustard differs from the wheat grain in where it stores nutrients. So, field mustard, dicotyledon, so it's got cotyledons by default, and how it differs from the wheat grain is that the wheats, we've seen the wheat grain, haven't we? It's over here somewhere. So there, it's being stored in endosperm. So here we go. So start with the wheat then. Wheat stores nutrients. We don't need to whiffle on because we're only talking about that. We don't need to give piles of differences. Stores nutrients in endosperm. Whereas, the nice comparative term there, because we're wanting differs, whereas field mustard stores nutrients in two, because it's a dicotyledon. Cotyledons. There we go. Oh, and on we go again. The amino acid sequence of the protein cytochrome, I'm thinking I'm going to have to do some counting now, has been used to investigate the evolutionary relationship. The table shows amino acid sequences of parts of the protein from three sources. So we've got wheat, barley, maize. Amino acids are represented by a single letter code. For example, G equals glycine. Okay. So, let's shade them in actually. That one's different. That one's different from those two. These are the same. That one's different. 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 That's different. E. That one's different. That one's different. That one's different. Okay. Explain why determining the amino acid sequence of proteins from different organisms can be used to show evolutionary relationships. This is just a simple statement, isn't it? The more closely related they are, straight from your notes, the more closely related the organisms are, the less differences there will be. In amino acid sequences. It's still being very noisy in the office, I have to say. Count the differences between the amino acid sequences from sources 2 and 3. So we're just looking at these two then, aren't we? So 1, 2, 3, 4. Perfect. Using the table above and diagram 1 on page 12 to conclude which source came from which species. So look at the diagram on page 12. What have I got? I've got maize, wheat, barley. Maize, wheat and barley. So obviously these two are sharing a much closer common ancestor there. So we'd expect less differences, and this one will be out on a limb. So 2 and 3 are obviously maize and wheat. And 1 and 2 are further away. So these two will... So this, going back, has a much more recent common ancestor. So that'll be the 9 difference. That'll be the 11 difference. And then these two will be the 4 difference. That makes sense. Okay. So biggest differences between 1 and 2. So 2 and 3 are clearly wheat and oh, we've got wheat, barley and maize. Read the question. Go back. Wheat, barley and maize. So these two are 2 and 3, and then this one is further away from that one. So that will be the 11 difference. Z to barley is 11. So 9 difference, what was that? Gosh, this is taking ages for me to sort out. If I'd read the question properly. 1 and 3. 2 and 3, so that'll be 3. That'll be 1, and that'll be 2. Does that work? 1, 3, 2. Maize, 1. Wheat, 3. barley too. Yay! Go me. Nope, still recording.